Let's look at the first derivative test in the multivariable case. So the first derivative test is a theorem that says that if we have a function with domain D and it's differentiable on that domain, and if it has an extreme point, so a local max or min at some point A inside the domain, then the gradient has to vanish there. So all the partial derivatives have to be equal to 0. So now here's how we use it to find the maximum or minimum of a function. Let's take our function to be a quadratic polynomial in x and y. So it's got degree 2. It'll be x squared plus y squared minus 2x minus 6y plus 14. Okay, so in this situation, there's no domain given. So we just assume that it's the biggest domain, which makes sense. And that would be R2 for this function, because this function exists and is continuous everywhere. And so in particular, in this case, there's no boundary to think about or worry about, because the domain is the entire plane. Okay, so to find the gradient, we look at the partial derivative. So the partial with respect to x is going to be 2x minus 2. And then the partial with respect to y is going to be 2y minus 6. And then we're going to set each of these equal to 0, because that's what you do for the first derivative test. So this is, we set those equal to 0. And then the first equation tells us that we have to have x equal to 1. And the second derivative, or sorry, the second equation tells us that we have to have y equal to 3. And so from this, we only get 2 points. And so we know that 1, 3 is the only critical point. The derivative is, the gradient is non-zero everywhere else, and there's no points where the gradient fails to exist, because this function is differentiable everywhere. And so then let's see. We'll look at the second derivative test in a moment, but for now we can actually see that this is a minimum by rewriting the function slightly differently. So now that we see this magic point 1, 3, maybe you notice that if we complete the square, we have, let's see, I can rewrite x squared minus 2x, and then I'm going to add in a 1, and then I'll have y squared minus 6y, and then to complete the square here, I'll have plus 9. So the constant term that's left is just 4. And then if I rewrite this again, it's x minus 1 quantity squared plus y minus 3 quantity squared plus 4. And this has the form of a paraboloid. It's just got a vertex at 1, 3 instead of at the origin, like the examples we looked at before. So if I were to graph this sucker, so here's x, here's y, here's f. So I go out to 1, 1, 2, 3, and over this point right here is where our paraboloid is oriented. And so I would go up to height 4, and we'd have some paraboloid opening in a positive direction, because both of the x and the y term are both the x squared and the y squared term both have a positive sign out in front of them, so it's going to be opening upward. And so we can determine from all that this point right here is going to be the minimum value, the minimum of the function. So 4 is the absolute minimum of f. It is also a local min. And then we also can see that there is no maximum value of f. The value of f just keeps on increasing as you go further away from this 0.13. The value of the function just increases off toward infinity. So there's no max.